Given a graph of any function, for example, the functions that we have here, we can be able to sketch the gradient of the function without even knowing what the function is. Now, before I discuss that, I just want to take you back to what I had discussed in previous videos. And the idea is that the derivative of a cubic function is a quadratic. So the derivative of a cubic function is quadratic. So, for example, what this means is if we have this cubic function, f of x is equal to x cubed minus 6x squared plus 9x plus 1, its derivative will be 3x squared minus 12x plus 9. Now, note that this is a cubic function and this is a quadratic, which means if we are given a graph of cubic function, we can be able to sketch a graph of a quadratic. Okay, so we can be able to sketch. It won't be exact, but it will be close to what the graph of its derivative will be. So back to this question here. So here we have two graphs, and these are cubic functions. Okay, these are cubic functions, and we want to sketch the graphs of their derivatives below here. Now, so let me start with this point. At this point here, we can see that the slope is 0, which means it will be somewhere here. Okay. Now, if I pick this point over here, this point, we can see that we are going uphill. The gradient is positive, which will be somewhere here. Okay. Now, the gradient of another point here will be positive because you're going uphill, which will be somewhere here. And then we know that our graph will be a quadratic anyway, so we can go ahead and sketch it, and it will look something like this. So something like that, because we know that the graph of this function will be a quadratic anyway. Okay, and if you look at the left of the derivative, you can see that the slope is positive but reducing, and that's why we are going down. Reducing, the slope is reducing to 0, but it's positive, and then it increases again. Okay, now on the right, what we have is a situation whereby at this point here, the slope is 0, so there, and then at this point here, the slope is negative because you are going downhill. Okay, so it's negative. It's somewhere here, somewhere there, and then at this point here, the slope is negative as well. Okay, so it's somewhere there, and starting from the top, we are always going downhill, but it's a high negative gradient, keeps on reducing to 0 and then again negative, which means our function will look something like that. So what you're saying here is that on the left hand side, we can be able to sketch, in general, we can be able to sketch the graphs of these functions that we have here, these cubic functions, and we end up with quadratic functions. Now, suppose I label this point here P, and this point Q. Okay. So this will be the corresponding x coordinates. Okay. And another thing is that on the left of this gradient function, on the left here, we can see that the slope is reducing, which means on the left, the slope of the slope will be less than 0 because it's reducing. On the right here, the slope of the slope will be greater than 0 because it's increasing. Okay. Now, how about on the next graph? We can notice here that um, at this point here, the slope of the slope is increasing, so that's greater than 0. And here, the slope of the slope is reducing, so less than 0. So there's change in concavity in both cases. Another thing that we can notice is this. Okay, so if you consider these 2 points, this point and this point, okay, we can notice that at this point, the gradient is equals to 0. Okay, look at point P and Q. Okay, the gradient is equals to 0. And we can also notice something else. At that point, point P and Q, we can see that the gradient of the gradient, because look at the gradient function for both cases. At point P and Q, the gradient of the gradient will be 0. Okay, the gradient of the gradient will be 0 at each of these points here. The gradient of the gradient is equals to 0. So what are some of the key points that we can be able to generate from these observations here? So one, we can say that, so these are the key points. One, we can say that at point P and Q, the first derivative is equals to 0 and the second derivative is equals to 0. Okay, so at point P and Q, the first derivative is equals to 0 and the second derivative is equals to 0. Something else you can notice is that at point P, concavity changes from concave down to concave up. At point P, concavity changes from concave down to concave up. Okay. Another thing we can notice is that at point Q, concavity changes from concave down to concave up. At point Q, from concave up. So this is very important, and we are going to use these key points to come up with a general statement that can help us in future to be able to determine if a point is stationary point or if it's not a stationary point. So we can say that in general, okay, so in general, if there's a stationary point of inflection at x is equals to c, then the first derivative at that point should be equal to 0 and the second derivative should be equal to 0. And concavity also has to change at that point. So if there is a stationary point of inflection, at x is equals to c, then the first derivative at that point should be equal to 0. The second derivative should be equal to 0. And concavity has to change.